Okay, well, the final is on Monday at 10:30 to 12:20. They're designed as 2 hours, so you'll have a full 2 hours. If you want to start before 10:30, I'll be in here from 8:30 on, so whenever you're ready, come on in. You will be allowed one sheet of paper, front and back. You can put whatever you want to on it. I would suggest lots of formulas and those kind of things, but now should I specify this is 8.5 inches by 11 inches, so I don't want a big old poster board coming in here. Got my units on there. Okay, and for the final there are 20 problems, so about the same size as a regular unit exam. At least most of them were 20 problems, but a few of the later ones, big problems, had a little bit fewer number. So we'll talk about what to expect on the final, kind of review, remember some of the things we did at the first of the year that maybe we haven't done for a while. But best way to study for these, go over your old unit exams, and we'll go kind of test by test to talk about the content. So the first test, we did a lot of limits. Find the limit, evaluate the limit. A lot of that was mainly a lot of algebra, simplifying algebra. Maybe it was factoring and canceling out the common factors. But the very first thing we need to do when we evaluate limits, plug the number in and see what we get there. If we get some valid answer, then that is the limit. But if we get 0 over 0, what does that usually mean? We got more work to do. And that's when you look at, well, can I just factor this and cancel the factors? Limit operations, factoring was probably the most straightforward. Also, we looked at complex fractions and the way we simplify that. One in particular, number 2 on the test, to remind you what complex fractions are. This, and then as x approaches 4, well, we'd have 1/3 minus 1/3 in the numerator, 4 minus 4 in the denominator, so 0 over 0. Now, what do you do to simplify this? A couple different things we could do, but the quickest way is multiply the top and the bottom by the least common denominator. And the least common denominator of our fractions, well, is going to be 3 and x minus 1. And as we multiply that top and bottom, 3 times the quantity x minus 1 times the fraction 1 over x minus 1 would leave us with just 3 for this spot. And then minus 1/3 times this, the 3's would cancel, and we'd have that. And that would be what's left in the numerator. The denominator, you have the x minus 4, and then times your least common denominator. And from there, we would get, ooh, this is a tricky one, 4 minus x over x minus 4 times 3 times x minus 1. Do we have a common factor here that we can cancel? Almost. 4 minus x, we would need to turn it around to negative 1 x minus 4. And then finally our x minus 4s would cancel. And you plug in x equals 4 now and we get our limit value. So complex fractions, a little bit more work, lots of algebra. Any of these techniques, there's lots of algebra to do. Another algebraic way for these limits, dealing with square roots. And in this case, well, number 5 from test 1, we've got the square root of x plus 4 minus 3 all over x minus 5. And again, quick check, we do end up with 0 over 0. But with this one, what we end up doing is what's called rationalizing the numerator. To be able to do that, we need to look at the numerator, multiply by the conjugate, top and bottom. Oops, not ready to do that one yet. And as you multiply that out, well, don't multiply the denominator out, but multiply the numerator, we get x plus 4, then plus 3 times that square root, minus 3 times that square root, so the square roots cancel, and then minus 9. Well, what's that turn out to be in the numerator? X minus 5, so the x minus 5 cancel with that. We're left with 1 in the numerator over that denominator, and now we can plug in the 5 and get our value for the limit. So lots and lots of algebraic ways to evaluate limits. Those are the 3 main ones. Okay. And we also looked at evaluating a limit from a graph. And problems 10 and 11 talk about that. Not only what's the limit as, say, x approaches 2, but we may look at what's happening as x approaches 1 from the right or x approaching 1 from the left, something like that. So look those over. And we talked about continuity. Where is a function continuous or where is it discontinuous? And that usually, well, if we had a fraction, that was where the denominator equaled 0. So factor out your numerator and denominator. And then number 12, our factors ended up, we'll do the quick version on this. Now, this function would be discontinuous at x equals -7 and at x equals 5. But what's different about these discontinuities? notice in the top we have an x minus 5, the bottom. So at x equals 5, this is where we'd have a removable discontinuity. And later on in when we started graphing in detail, we would have a hole in the graph at this x equals 5. We'd have a vertical asymptote at x equals -7. So this was kind of the laying the groundwork for later on with the graphing holes and asymptotes. But that's the continuity. And then we also looked at piecewise defined functions, whether they're continuous or not. And that's basically check where the pieces split, see if at that x value, if they end up being the same function value, then it's continuous, but if they're different function values, then they're discontinuous. In test 1, we looked at a lot of different applications. Now, we've seen a lot of applications through the semester. Not everything is going to be on the final, but it is a possibility that these applications would be there. Of course, we've introduced this, the average velocity and then instantaneous velocity. Instantaneous velocity, now we know, is just the derivative of the position function. We're just doing that, working with that in this last chapter, going the other direction. But here we'd start with the position function and find the velocity. It'd be the derivative. Also, in this first test, we looked at slope of the tangent line. Of course, we've been using that later on as well. But on these applications, test 1, we were using the definition of the derivative. On the final, any of the applications, I will let you, derivative, not. On the final, I will let you use the shortcut derivative formulas to find, if you need to find the velocity, take the derivative of the position. But also on test 1, we looked at calculating the derivative of a function using the definition. That will be a possibility on the final. This may be one problem, using the definition of the derivative. Find f primed of x. And do you remember what the definition is? Limit as delta x approaches 0 of f of the quantity x plus delta x minus f of x all over delta x. That would be a very good formula for you to have on your sheet of paper. Okay. But I'll give you a function and have you find the derivative using this definition. Most of it turns into a huge algebra problem. We do just a little bit of calculus at the end, taking the limit, which you found most of the semester, the biggest part of the problems have been algebra. Okay. So that's test 1, mainly finding limits, continuity. These definitions are the definition of the derivative, and then the applications, which any application, I'm not going to expect you to use the definition. But there will be a problem where I state use the definition of the derivative. So there will be one problem like this. You'll need to be able to do that. Okay. Questions out of test 1? Okay, test 2. Bunches and bunches of derivatives. Find the derivatives using the shortcuts, the formulas, power rule, product rule, quotient rule, chain rule, all those rules. And then we have the trig functions, log functions, exponential functions. Okay, so excuse me. The final could see any of those types of functions. It'll be probably not just one, but maybe 2 or 3. Find the derivative of, and of course, probably won't be the easiest one, but it's not going to be find the derivative of x squared, but aw shucks. But by now, you guys have those derivative formulas down pretty good. Now remember, the derivatives of logarithms, the natural logs, we can use log properties to rewrite the function to make the derivative finding it a lot easier. So keep that in mind if you run into a log function. So test 2, that was pretty much it. Find the derivative. Now we did look at a few details on that. Evaluate a derivative, number 14. 15 and 16 were find the derivative of an implicit function or implicit differentiation. Make sure you know how to do that. And then using implicit differentiation, number 17 was find the equation of the tangent line. So first off, we'd have to use implicit differentiation to find dy by dx, which dy by dx turns out to be the slope of the tangent line. And in something like that, you'll be given a particular point. You can plug in the x value and the y value, and m will be your derivative at that point, and then plug it into your equation of the tangent line, point slope form. So that's one way of using the implicit differentiation. And then one more time with the applications, position function, find the derivative is the velocity, derivative of the velocity is acceleration. So again, lots of applications that could come from that relationship. Okay. Any questions over test 2? Okay, and test 3, I think, was everybody's favorite test, right? Probably not. But lots and lots of different applications of derivatives. And for this, I will limit a little bit. Some of these get real specific. So for the final, there will not be any linear approximation, which for test 3, problem number 1, nor Newton's method, approximating the solution of an equation. Nothing like that on the final. That's number 2 out of test 3. But 3, 4, 5, those applications are definitely possibilities. Optimization type problems, find the maximum area, find the minimum surface area, maximum volume, those types of problems. Related rates, a lot of those ended up being right triangles, and x squared plus y squared equals r squared, and taking the derivative of that. Implicit differentiation, knowing the rate of one part, what's the rate of a different part. So those types of applications, definitely possibility for the final. That was optimization, related rates. And then after we did those, we really got into how the derivative helped us out in identifying graphs and what the function was doing in certain places. So the last part of this test, we did lots and lots with graphs. Maximums, whether it's an absolute maximum or minimum over a certain interval. Now, because we're restricting it to a certain interval, the maximum or minimum may occur at the endpoints, but also could occur at critical points. Okay, critical points where the derivative equals 0 or the derivative is undefined. Also, with the graphing with maximums and minimums, we can find local maximums and minimums, or sometimes we call those relative maximums and minimums. Again, those would occur at critical points. So be able to find your critical points, and then whether or not we have a maximum or a minimum, or perhaps neither, from a critical point. Also from that, first derivative will tell us whether we have increasing or decreasing interval. Okay. What tells us about concavity? Second derivative, concave up or concave down. Okay. So increasing would be where the first derivative is positive. Second derivative is positive, is where we'd have a concave up curve. Negatives would be decreasing or concave down. So we did a lot of stuff with those. One more problem from test 3 that will not show up on the final. Number 10. This is where, given the graph of the derivative, tell us about where the maximum or minimum is, where is it increasing or decreasing. we will not have anything like that on the final. But the last three problems, 11, given certain properties, sketch the graph. And this could be where the derivative at some point equals 0, or where the derivative is less than 0 for some interval, where the second derivative is greater than 0 for some interval or at some point. So a lot of generalization here. Draw a graph that fits all these conditions. So again, it's more of critical points, okay, where the derivative equals 0, or concavity, the second derivative is greater than 0, that portion of the curve would be concave up. A lot of details like that. And then 12 and 13 out of test 3, we finally got to the particulars of where a function is discontinuous and looking at vertical asymptotes and horizontal asymptotes. Mentioned earlier from test 1 where it's discontinuous. Well, if it's removable discontinuity, we have a hole in the graph, but if not, then we'll have a vertical asymptote there. And then the horizontal asymptotes are basically comparing your degree for your polynomial in the numerator to your denominator. If they're the same degree, like number 12 is, then you'll have y equals, and then your coefficients, 3/2 in the case of number 12. But if the degree in the numerator is less than the degree in the denominator, then y equals 0 is your horizontal asymptote. And now in class we did a little activity. If the numerator has a higher degree than the denominator, then that's an oblique asymptote. But oblique asymptotes will not show up on the final, so don't worry about those. Okay, test 4. Well, hopefully that's still a little bit fresh in your mind. Working with antiderivatives or indefinite integrals, and then moving on into the definite integrals. But a lot of it, first part of it was indefinite integrals, the antiderivatives, and again, all the different formulas for those. And make sure you know how to do substitution. We do a lot of integration by substitution. So, one type of problem that shows up on test 4 and on test 5 that will not be on the final: no solving differential equations. So test 4, number 7, and then again test 5, when we get to that, number 3. Nothing like that will show up on the final. But the process, you should be able to do the process. It's basically what you're doing in the other parts of test 5 in the application of acceleration and velocity and position function. But now, once we did the antiderivatives, then we moved to introducing or building up to the definite integral. And first off, we looked at area, estimating area under a curve using rectangles. So possibility there, whether it's using left endpoints or right endpoints. N equal 4 rectangles or 8 rectangles, Well, I'll make sure it's a smaller number of rectangles so you'll have time to get done with the test Monday. But there won't be like 8 or 16 rectangles, but probably around 4. Find your delta x and find the x values, and then length times width. The length of each rectangle will be a function value at either the left endpoint or right endpoint, and then your width is your delta x. Okay. So estimating area using rectangles, definitely a possibility. Now this, along with summation and the limit process, led us to the definition of the definite integral, but for the final there will be no definition of the definite integral. So that was number 9. Okay. And then also no number 10, which dealt with the fundamental theorem, one part of the fundamental theorem, the derivative of an antiderivative. We're not going to do anything like that. But definitely the other part of the definite or the fundamental theorem of calculus, that is a major part of what we do. So that's basically from the number 11 on, we're dealing with that fundamental theorem. So evaluating a definite integral, definitely a possibility. And again, that's your integral from a to b of f of x dx. We find the antiderivative function, and then we evaluate it f of b minus f of a. Now, some of you have been getting these turned around. You go f of a minus f of b, but it's the top one first and then minus the bottom one. But that evaluating definite integrals, we've done lots of that. Find area under a curve and above the x-axis. We introduced that in test 4. Test 5, we kind of expanded on that quite a bit, area of some region or area between two curves or something like that. But it all started out, test 4, area under some curve and above some x interval. Now, number 18, we looked at a graph. Let's see, how do we put this? No evaluating an integral based on a graph. So nothing like number 18 from test 4. Oh, excuse me. And also nothing using the trapezoidal rule or the Simpson's rule. None of those approximations. That was 19 and 20 out of test 5. Yeah, with test 4, nothing with 18, 19, and 20, nothing like that on the final. Okay, and finally test 5 should be real fresh in your mind. applications of integration. Again, the acceleration, integrate to the velocity, which integrate to the position function. And we just saw lots and lots of different types of problems there, be able to work through those. Then again, number 3 was the solving the differential equation. We already said nothing like that will show up on the final. Number 6, we talked about finding the average value of a function, but there's no problem like that on the final. Area, well, test 4, we introduced area of a region. Test 5, we expanded on that. Definitely something like that will be on the final. Between two curves, or area of a bounded region, maybe 3 or 4 equations, and we got to find what integration represents that, and also whether it's y equals some function of x, or maybe it's x equals some function of y. A couple of the problems on test 5 dealt with x equals some function of y, so make sure you're able to kind of flip that around and look at it horizontally rather than vertically. So that is the review for the final. Any questions?